Welcome everyone to today's Explainer. We are jumping right into a seriously fascinating journey into the absolute heart of modern manufacturing. We're going to trace the entire path, starting from the big picture concept of taking a raw chunk of material all the way down to the microscopic, high-stakes precision of cutting metal. So let's dive right in and explore exactly how the massive, ultra-reliable machines of our modern world are actually shaped, literally, one tiny metal chip at a time.
Here's our game plan for today. We're going to run through the basics of manufacturing processes, check out the cutting tool arsenal, figure out how to actually select the right tool, dive into the science of chips, tackle heat and fluids, and finally wrap up with measuring for precision. We'll build this mental model step by step.
All right, part 1, basics of manufacturing processes. Let's set the foundation.
So at its absolute core, a manufacturing process is just the method we use to transform raw material into a finished good. Pretty simple, right? But it basically splits into two camps. First, you've got non-cutting, or chipless processes. Think forging or rolling, where metal is shaped by pure force and heat, without actually removing any material. And then, you have the cutting, or chip-forming processes. This is where we get our exact shape by aggressively tearing away unwanted material from the workpiece, which flies off in the form of chips. And that chip-forming process is exactly what we're zeroing in on today.
Now, you might be wondering, how do engineers actually decide which process to use? Well, it's a huge balancing act. They have to weigh several crucial factors like the material's properties, the complexity of the product design, and the production volume. For example, if you're making 1,000,000 of something, high-volume production might totally favor casting. But if you need incredibly high precision and super tight quality tolerances on a really complex part, you are definitely going to choose a cutting process, like CNC machining. It's this constant tug-of-war between cost, efficiency, and precision.
Moving right along to part 2, the cutting tool arsenal. Let's look at the actual instruments doing the heavy lifting.
Let's break down the anatomy of a single-point tool. This is a cutting tool that just has one cutting edge at the end, which is super common for operations like turning on a lathe. The main bulky body of the tool is called the shank. Now, the actual cutting part isn't always just the same piece of metal sharpened down. Actually, it's very often a highly specialized insert, or tip, that gets mechanically clamped or brazed onto the shank. You've also got to factor in the overhang, which is just how far the tool sticks out from the holder, as well as the specific geometry of the tip itself, like the side rake angle and that tiny microscopic curve at the very tip, known as the nose radius.
Okay, so what are these tools actually made of? Well, it entirely depends on what you're trying to cut. If you're machining softer metals, say aluminum or copper, you can easily get away with high-speed steel. It's got high toughness and handles moderate speeds really well. But step up to stainless steel, and you're going to need carbide for its intense hardness and heat resistance. And for seriously hardened alloys, you might literally have to use ceramic tools. Ceramic is ultra-hard, but it's brittle, meaning your machining setup has to be perfectly stable. Matching the right tool material to your workpiece is an absolutely high-stakes decision.
Just a quick historical aside here. Carbon steel is actually the oldest tool material we have, but it has a fatal flaw. It has terrible hot hardness. Basically, it loses its sharp edge the second things get too hot. High-speed steel, or HSS, completely revolutionized the industry by adding alloying elements like tungsten, chromium, and vanadium. That metallurgical recipe massively increased wear resistance, meaning the tool could stay hard even when it was literally glowing hot from friction. A real game changer.
That brings us to part 3, selecting the right tool. We know the arsenal, so how do we choose?
It really boils down to a massive chain reaction of variables. Think of it like a cascading set of decisions. The specific workpiece material you start with directly dictates your cutting speed, your depth of cut, and your feed rate. Then, those exact parameters, combined with the geometry of what you're trying to make, dictate the required cutting material, the exact shape of the insert, and even the specific tool holder you need. Every single variable is intimately linked to the others.
And when a machinist evaluates that workpiece material, 3 physical properties reign supreme. Number 1 is hardness. Obviously, as the workpiece gets harder, your tool must be even harder to resist wearing down. Number 2 is toughness. If you're cutting something like cast iron, which creates these bumpy, intermittent forces, your tool needs the toughness to not just shatter on impact. And finally, thermal conductivity. This is huge. Materials like stainless steel have very low thermal conductivity. That means they don't absorb their own heat well. So all that massive thermal energy just pools right there at the cutting zone, threatening to literally melt your tool.
Let's move into part 4, the science of chips. We're zooming right into the cutting zone now.
We usually think of cutting metal like a sharp knife slicing cleanly through butter, right? Well, actually, scratch that. That's entirely wrong. Machining is a violent shearing action. Think of a massive snowplow forcing a huge layer of packed snow up and over its blade. As the cutting tool advances, it forces a small amount of the metal to literally fracture and shear away along a very specific plane. And that sheared-off metal, that is what we call a chip.
Now, when that shear happens, you generally get one of two main types of chips. The first is a continuous chip. It looks like a long, unbroken ribbon with a smooth, shiny surface, and it usually happens when you're cutting ductile, softer materials at high speeds. The second type is a discontinuous or segmental chip. In this case, the metal fractures into fairly small, separate, jagged chunks.
Now, instinct might tell you that a smooth, continuous ribbon is better. But counterintuitively, that jagged, discontinuous chip is actually a machinist's best friend. Why? Because long, unbroken ribbons of razor-sharp metal flying around at high speeds are incredibly dangerous. They can tangle around the tool, whip around and scratch up your perfectly finished part, and they are an absolute nightmare to clean up. Discontinuous chips just break off and fall safely away into the pan.
So, keeping chips under control is absolutely crucial. But sometimes things go terribly wrong right at the cutting edge, creating a phenomenon called a built-up edge, or BUE. When you're cutting ductile metals at lower speeds, the extreme heat and pressure can cause a pile of compressed metal to literally weld itself to the tip of your tool. It forms this weird, false cutting edge, and eventually this highly strain-hardened lump just snaps off, taking chunks of your expensive tool with it and leaving a profoundly ugly, rough finish on your part. No good.
To stop those dangerous continuous chips from forming in the first place, modern tools use these clever mechanical designs called chip breakers. Their entire job in life is to force those long chips to curl up and snap into safe, tiny pieces. There are three main types. You've got a step type, which is just a ledge ground directly into the tool face, a groove type, which is a small channel right behind the edge, or a clamp type, which is literally a physical metal plate screwed right into the path of the chip to force it to curl back on itself and break.
All right, part 5, heat, friction, and fluids. Let's talk about cooling things down.
With all this metal tearing, sharing, and flying around, you are generating a massive amount of thermal energy. To combat this, we flood the zone with cutting fluids. And these fluids play a dual, totally life-saving role for our tools. First, they act as a coolant, carrying away the immense heat generated by the deformation of the metal, which keeps the tool from softening. Second, they act as a high-pressure lubricant. By squeezing into the microscopic gap between the tool and the chip, they reduce friction. This lowers the power needed to cut and is the primary way we prevent that disastrous built-up edge we just talked about.
Finally, let's zoom all the way out for part 6, measuring for precision. Because honestly, cutting metal perfectly doesn't mean a thing if we can't prove it's perfect. In the world of CNC machining, the precision requirements are just staggering. Verifying an outer diameter or a tiny inside keyway often requires an accuracy of 0.001 millimeters. To put that into perspective, an average human hair is about 50 times thicker than that. That is wild. To achieve this, quality control relies on highly specialized, beautiful instruments like outside micrometers, vernier calipers, and custom thread gauges.
So how do we actually read one of these things? Let's break down the math on an outside micrometer. It's actually a pretty cool system. Step 1. You note the minimum range of the specific micrometer you're holding. Let's say it starts at 50.00 millimeters. Step 2. You read the main barrel, which in this example shows 13.50 millimeters. Step 3. You look at the rotating thimble, which points to the number 13. You multiply that by the tool's least count, which is just its smallest readable unit, 0.01 millimeters, giving you 0.13 millimeters. Finally, step 4, add the whole shebang together. 50 plus 13.50 plus 0.13 gives you a final, ultra-precise reading of 63.63 millimeters.
But, as any veteran master machinist will tell you, there is an economy of measurement. You don't just grab the most complicated, ultra-expensive laser tool for every single job. You always have to select the optimal gauge that perfectly achieves the required accuracy without adding unnecessary complexity or slowing down your production line. It's all about finding that ultimate balance between perfection and efficiency.
And that wraps up our explainer for today. But before we go, I want to leave you with this thought. Every single airplane you fly in, every car you drive, every medical device used in a hospital relies entirely on these fundamental principles.
How is it that these incredibly tiny mathematical tolerances, calculated at the microscopic, shearing edge of a cutting tool, ultimately shape the massive, reliable machines of our modern world? It's a pretty amazing testament to the foundational science of manufacturing. Thanks so much for joining me on this journey today. Keep learning, keep exploring, and I'll catch you on the next explainer.